connect two computers together and exchange data via just the physical layer, the data link layer, and we have seen how this works just now in the last presentation. The two computers can communicate via direct cable. If we have switch or hub, we can connect several computers together still in those layers. However, if we want to connect computers that are far away from each other and have many computers in between and many hops that the packets need to pass through in between, then we need some additional logic to be able to do that, and this logic is implemented in the network layer. So in the bits, in the first layer we were just sending bits. In the second layer we're sending frames, and here the unit is called a packet. So the network layer is concerned with getting packets from the source all the way to the destination, no matter where this destination is in the world. Concerned with getting packets from source to destination. Including many hops in between. These hops are also called intermediate routers. So that's the difference between what the data link layer does, because the data link just moves frames from one end of the wire to the other end of the wire. So if we have many routers and machines or many networks in between, then we need some more complicated logic that we need to implement. So in order to achieve this goal, the network layer needs to know needs information about the topology of the network. By topology, we mean the physical location of all the links and routers, their physical geographical location which compose the networks that are part of this network. The network layer must know about the topology of the network, which is the geographical locations of the routers and links on this network, not to overload the network with the packets that it sends. So that's something that the network layer is concerned with. Not to overload the network. And it has to deal with differing networks on the way. So it's one thing in the data link layer to send data from one computer on one side of the wire to another computer on the other side of the wire. But if we have to send the packet from here to China and has to go through not to another continent and through many possible networks in between, then these networks might have different configuration parameters than our network and than other networks on the way. And so this network layer has to examine the particular types of networks and their properties and their configuration parameters as the packet reaches them. And it needs to adapt dynamically to those properties and make the packet able to pass through that network. For example, if the packet has a particular size and it reaches a network which has a smaller maximum size transfer unit, then that packet is too big to go through that network. So the network layer has to examine all of these parameters, and if the packet is too big, then it will just split it into two pieces or two or more pieces. Whatever the properties of the particular network that the packet is passing through, this layer has to do with these different networks and adjust to them dynamically. So some design issues, what this layer has to do. So several things we will look at is the first one is store and forward packet switching. The next one is the service provided to the transport layer. So remember that every layer, the function of every layer is the main goal of each layer is to provide service to the layer above. So the network layer provides service to the transport layer. So service is provided to the transport layer. Connectionless and connection-oriented service and a possible virtual circuit. Now, we don't use this virtual circuit and connection oriented much in this layer. This is done in the next layer, in the transport layer, but theoretically it's possible to do it in the network layer. So we could look at it as an option, but in practice it's not used because most of the communications done in this layer have no connection. So we will mostly focus on connectionless service provided in this layer. So let's look at the store and forward packet switching. So this is just showing some of the major components of each network are owned by the internet service providers. So this is the internet service provider's equipment. And these things, A, B, C, G, E, are routers which are owned by the internet service providers, and the links that connect them also, the lines. The customer's equipment equipment is outside of this oval. So this is the internet service providers, and these are the customers. So this is some home computer called host 2, and this is a personal router of that customer. And then we have another customer at host 1, which is outside of the internet service providers. So the way this store and forward packet works, this customer is directly connected to one of the routers in the internet service providers, while the other one has an intermediate router in between, which is connected to the internet service provider's router. So when the first host has a packet to send, it just transmits it to the nearest router. Then the router gets it and stores it briefly and examines it, that it's complete and that it has received all the parts of this packet. And once it has them, it forwards it to the nearest router. Along the path, the nearest router along the path until it reaches the destination. So in this case, well, first the path has to be calculated. Which path is it going to go through? So this router has to make a decision of which path to choose. So the host 1 wants to send the packet to host 2, so it can go either A, C, E, F, or it can go A, B, D, E, F, or it can go A, C, D, E, F. There are several possible routes it can take. So each one of these routers has a routing table which contains information about the routers that are directly connected to it, and if a packet arrives with a certain destination, which line it should give it to. This is similar to that project which I've signed. It's just comparing the packet that comes to a routing table, and based on what the table says, it routes the packet on the appropriate line. Now, in this particular example, the host 1, there's a process. It could be a web application, it could be an email, it could be sending some very long email, or email with many attachments to it, and it's too big. So it's 4 times bigger than the maximum transfer unit of this particular network. So the network layer will break this packet into 4 pieces. So it has piece 1, 2, 3, and 4. And it will just start by sending the first piece. So first piece will be sent from host 1 to router A, and every router has an internal routing table which shows. So the host 1 wants to send a packet to host 2, the destination router is F. So the first router is going to look in its routing table and says destination is F. So output this packet onto line C. So it's going to go from A to C. Next, C will get it. It will look in its routing table. Destination is F. So output this on line E. So it will output this on line to router E. Line means that there's a line that connects this router directly to another router. It's like it has a network interface card, which is part of some networks. So the router might be on many networks at the same time. Imagine router might have 50 network cards, each one on a different network. So every router has a table with all the networks and the lines that have connection to it. So we'll pick one of them. In this case, C. If it looks in the table for C, the destination is F. So line it sent on line E, so it sends it E. Then E gets it. E looks in its routing table. Destination is F. F is directly connected to it, so send it to F. And there you go. The first packet is there, and it made it to the destination. And so all the following packets, packet 2 will go the same route. 3 will go the same route. These are pieces of the packet. So something different happened to the piece number 4 because it took a different route. As you can see, all of them went ACE, but the 4th piece went ABD. Why do you think that is?
Too much information to fit through that router C, so adopts router B.
Okay, so I'm still saying, one of the things, design issues in this layer is not to overload the network. So maybe the network layer decided that it's too much traffic in this way. There is a congestion here, or there is an overload. So we decided to just take another route. You think that's possible?
Yeah.
It is possible. Well, these routers, each one maintains a routing table, but this routing table is not a static table that's just configured once and for all and it just stays like this forever. Kind of like, we had a question in the group, where's the routing table? And they say, well, we're hard coding it. It is possible that we can show it in the interface and then update it. If we need to, we should be able to update it because these are not static tables. These tables are dynamic tables that get constantly updated. So each router is receiving information about the routers nearby, or the ones that are connected to it, and what's going on these links. So if this particular router learns that there is a congestion on this way, it's going to update the routing table and say it will, from now on, if the packets are going to F, will head to the output on line C. Now they will be outputted on line D. So the routing table is updated when the 4th piece came in, and so the router routed it another way. What other reasons do you think there might be to update it in this way and change the route? One is that there is a congestion. Could you think of another reasons why we don't want to go through that route anymore? Yes.
One of the routers could have died.
That's an excellent example. The router's dead. It crashed. It's not there anymore. So ping the router. It doesn't exist. What happened to it? We don't know, but it's not there. So we can't send it this way. We have to forget about this link. It's not going that way. Pick another route. The router's dead. Okay, it could have crashed, or it could be physically destroyed. There might be a war and the router was destroyed. Or there might be an earthquake and the router fell underneath least the earth, or it might be rats chewing on the wires. That happened, and the router is dead. So there could be many reasons why we don't want to go this route. This particular design, connectionless, there is no connection, is named, the packets are here named datagrams. The reason they're named datagrams is with analogy of, because the way this works is analogically to what the post office is doing. And when the post office has to send a telegram, it does exactly the same thing as what we're doing here. So in analogy with the telegram, they named these packets datagrams, because the post office will do exactly the same thing that we just discussed when they have to deliver a package. Okay, imagine that the package, the post office truck has a package and it has a sender address, a receiver address, and the truck is taking like I-85 to arrive at the destination address. However, once it got on I-85, it was stuck there because it was a lot of cars and it was a traffic jam. And then there was a big sign that said, there's an accident, there's delay, take an alternate route. Consider alternate route. So the post office truck will get off of the I-85 and just take another road to deliver the package. So if one of the routes becomes unavailable, or it's congested, or it has a road construction, or it's got another issue, then just pick another route. This was the original design of the internet. Why we invented this internet at all is because there was an advent of a Cold War, and we wanted to be able to survive the nuclear war where some of the machines would be physically destroyed. So if one of the paths become unavailable, that should not affect the entire network. We should be able to take an alternate route and still deliver the packet, even if one of the routers is dead. That's not going to affect the delivery of our packet. In the layer 3, the network layer, where we have the IP protocol, the internet protocol, there are no connections. Most of it works like that, well, what we see here. There is no guarantee that the packet will get there. Some of the routers might get the packet, and if they have too many packets, they can drop it because they have congestion and they need to alleviate the congestion somehow, so they drop it. If that happens, the packet will not make it. There's no guarantee, there's no connection, and that's what the IP does. It is possible to implement a connection if we want to, though this is not done, as I said, in this layer, but theoretically it's possible if we implement a connection. Then we would have a dedicated connection to each packet and the route that it goes through, and all the packets that go through this route will follow that connection. This will be called a virtual circuit because its analogy system does. So the first, the connectionless, was analogical to the post office delivery truck. The second one, which has a connection, is analogical to what the telephone system is doing. It creates a circuit, virtual circuit. You know, when we're going to talk on the phone, first we need to establish connection to the other person that we're going to talk to. So we call them and have to connect to them. And once the connection is established, we can talk. And everything that we say goes through that connection from the sender to the receiver. If when we're done talking, we have to hang up and close the connection. We don't want to use any more resources. We're done talking. That same situation happens if there's going to be a connection with the packets that we're sending first. There has to be established connection between the sending machine and the receiving machine. We choose a path, and we always follow that path for all of the communication that goes between the sender and the receiver. The idea is to avoid having to choose new route with every packet that we send out. Whenever the connection is released, then this virtual circuit is terminated. So, for example, host 1 wants to send a packet to host 2, then establish a connection with it and assign identifier 1. So all the packets that go from host 1 to host 2 would use connection identifier 1. If host 3 wants to talk to host 2, then we give another connection number 2, and all the packets use that connection number. The connection number is recorded as the first entry on each of the routing tables on the path. So from host 1 to host 2, the path will be A, C, E, F. So we have it goes through for A, for E, and for C and F. They all have the connection 1 as the first entry in their routing table. Now, the telephone system does something very different from what the post office is doing, in a sense that it makes sure that there always are enough resources. So when you call somebody on the phone, there always are enough resources to be able to connect to that person at that particular time and talk to them. So the telephone system over-provisions resources. So if we have to compare then the quality of service will be difficult for the connectionless system, because we said that there is no guarantee, and the packet might not make it there, so we can't provide much quality. Congestion control would also be difficult. compared to the virtual circuit network, because we would always have enough resources, so we can, we're not going to have congestion, and we will not have issues with quality of service